Cloudflare just announced that they're adding container support to their serverless platform. Simple, scalable, and global, containers are coming to Cloudflare workers in June 2025. This is pretty exciting for me. It is almost the end of developer week, and we haven't talked about containers until now. As some of you may know, we've been working on a container platform behind the scenes for some time. In late June, we plan to release containers in open beta, and today we will give you a sneak peek at what makes it unique. Workers are the simplest way to ship software around the world with a little overhead, but sometimes you need to do more. You might want to run user-generated code, execute a CLI tool, use gigabytes of memory or more than one CPU core, or port an existing application as a container to Cloudflare without a whole rewrite. And this is really what I'm all excited about. I feel like I'm pretty sure Google Cloud is the only major cloud provider that does like true serverless containers via Cloud Run, because you can set up a container, tell it how it's going to be accepting web requests, and then configure how you want it to automatically scale. And it'll even be able to scale down to 0, which is the dream of serverless computing, is to only use and pay for exactly how much compute you actually need. But historically, doing full serverless has come with some major drawbacks, like these points that they've made here. I mean, just for an example, let's say you want to run an audio streaming platform. Well, you're going to need to run FFmpeg to actually process the audio into a streamable format that isn't uncompressed and all that good stuff. And you just can't do that with serverless today. You either have, not enough memory, not enough CPU, or you just don't have access to all of the full platform tools that you would in a full fat application. And even Cloudflare workers, for example, you have a CPU time limit of, I believe, 50 milliseconds, which is totally fine for REST API, but that's not going to do anything for anything more intense like transcoding or even AI workloads. So this is really exciting to me. I'm really excited that another cloud provider is coming out with first-class support for containers. Cloudflare containers let you do all that while being simple, scalable, and global. Through a deep integration with workers and an architecture built on durable objects, workers can be your API gateway, service mesh, or orchestrator. Instead of having to deploy new services, write custom Kubernetes operators, or wade through control plane configuration to extend the platform, you just write code. So actually, at this point, I'm actually a little scared of. I think Workers is a good product, but it is very much like you have to do it the Cloudflare way. You have to work with their Worker SDK specifically, whereas something like AWS Lambdas, you can give it like a Go binary, or you can just give it like a node project and have it run it for you. The drawback to me with Workers is that you really have to configure your project in a very Cloudflare Workers way, which makes me very hesitant on vendor lock-in. But let's see what this really is going to look like. A stateful workload, executing AI-generated code. Let's look at a stateful example. Imagine you're building a platform where end users can run code generated by an LLM. This code is untrusted, so each user needs their own secure sandbox. Additionally, you want users to be able to run multiple requests in sequence, potentially writing to local files or saving in-memory state. Yeah, and you can't do this with serverless computing today. To do this, you need to create a container on demand for each user session, then route subsequent requests to that container. Here's how you can accomplish this. First, you write some basic Wrangler config, and then you route requests to containers via your worker. And again, this Wrangler config, let's see on how the syntax looks. I'm a little put off by it, but let's just see. Okay, here's the code. So we're getting the container from the Cloudflare workers package, and we are exporting our class code executor, which is extending our container from Cloudflare. We're saying it's running on port 8080 and it should go to sleep after a minute. Okay. And then the only thing it does is it has a fetch function, which I'm assuming just responds to a regular fetch request. And then we're getting the URL. Okay, so this is some like routing. So that we're saying, okay, for this like REST API that we're setting up here, at route/execute code, we're going to grab the session ID and then messages from the body. And then we're going to call in our environment, which I also think is a Wrangler thing. We're going to say, okay, our AI service run this code, or I guess this model with our messages. And then we get a different container for each user session. So we get the ID from the name of the session ID. Okay. And then we set up a sandbox. We're getting a sandbox. And then we execute a request on the container. So we're saying, okay, in our sandbox, do a fetch request to our execute code with our post. Okay. And then we have the rest of our worker. Okay. I'm mostly following along. So let's see what it says. Then deploy your code with a single command, Wrangler deploy. This builds your container images and pushes it to Cloudflare's registry, readies the container to boot quickly across the globe, and deploys your worker. That's it. How does it work? Your worker creates and starts up containers on demand. Okay, so actually here, so this extends container, but is this technically a worker, or are we saying a container now is also a Cloudflare worker? So I guess you could have different types of Cloudflare workers. Each time you call the environment code executor with get ID with a unique ID, it sends requests to a unique container instance. The container will automatically boot on the first fetch, then put itself to sleep after a configurable timeout, in this case, 1 minute. You only pay for the time that the container is actively running. When you request a new container, we boot one in a Cloudflare location near the incoming request. This means that low latency workloads are well served no matter the region. Okay, so that's really cool. This is really cool because, I mean, also historically running like container workloads, you're mostly picking and choosing where you want those workloads to run because it doesn't have the serverless benefit. It sounds like they are distributing your container to their global infrastructure, and then it is on demand spinning up those containers based off of the location of the request coming in. And that is the dream state, and that's very exciting to me. Cloudflare takes care of all the pre-warming and caching so you don't have to think about it. Okay, cool. This allows each user to run code in their own secure environment. Stateless and global, FFmpeg everywhere. And again, FFmpeg is the use case here that I'm the most excited about because you can create some like really awesome workloads and have it be just totally serverless, and auto-scaling is just the dream. Stateless and auto-scaling applications work equally well on Cloudflare containers. Imagine you want to run a container that takes a video file and turns it into an animated GIF using FFmpeg. Yes, it's a great workload. Unlike the previous example, any container can serve any request, but if you still don't want to send bytes across an ocean and back unnecessarily, so ideally the app can be deployed everywhere. To do this, you declare a container in a Wrangler config and turn on autoscaling. This specific configuration ensures that one instance is always running, and if CPU usage increases beyond 75% of capacity, additional instances are added. Awesome, this is cool. I actually saw, well, this is similar to how Cloud Run handles their autoscaling. Although interestingly here, it says when you turn on autoscaling, it always keeps one instance running. Of course, this is going to be to prevent like just like a cold boot where you have to be waiting seconds to get that first response. But the downside here is, again, you lose out the benefit of serverless where you're not paying for a service that's not actually doing anything. So here you would always be paying for at least one instance running. But depending on the pricing, that might not be a big deal. Okay, so let's look at the Wrangler config. We have our containers. Our class name is gift maker. I hate the class name thing. pairing object-oriented programming with serverless infrastructure never makes me excited, but we'll see how they have this set up. Okay, so we have our image, which is just our local Docker file. So this is saying, hey, in our local project, build this Docker file and treat this as our container image. That's great. That makes it really easy. Instance type is basic, and then we can configure the auto scaling here. So here we have a minimum instances of 1, and it will auto scale once our CPU target hits 75. Something else to think about here is we might also want to scale based off of memory, potentially, or just, yeah, I'm curious if there's other options on controlling the auto scaling. I'm also curious if the minimum instances has to be 1 in this case. Like maybe you technically can do 0 and just eat the cold start if you want to do that. So to route requests, you just call environment gift maker fetch, and requests are automatically sent to the closest container. Cool. So here is another container example here, but instead in our fetch function that we're exporting, you could using the route make gif and then returning the environment gift maker fetch. So this is just a regular worker. Okay. So I think we're saying this is a regular Cloudflare worker responding to your fetch request. And then here is our gift maker class. So we have to have a regular Cloudflare worker to spawn our container. Okay, I'm curious if you also have to do it that way as well. If I'm not understanding this correctly, let me know in the comments. Okay, going beyond the basics. From the examples above, you can see that getting a basic container service running on workers just takes a few lines of config and a little workers code. There's no need to worry about capacity, artifact registries, regions, or scaling. For more advanced use, we designed containers to run on top of durable objects and work in tandem with workers. Let's take a look at the underlying architecture and see some of the advanced use cases this enables. Durable objects is programmable sidecars. Routing to containers is enabled using durable objects under the hood. In the examples above, the container class from Cloudflare Workers just wraps a container-enabled durable object and provides helper methods for common patterns. In the rest of this post, we'll look at examples using durable objects directly, as this should shed light on the platform's underlying design. Okay, so we have our external requests. We can either be in North America or Asia. You can have global requests coming in, and here coming in and hitting our workers platform. So it's dependent on where the user is. They're coming into the worker closest to them, and then that worker is then reaching out to the closest durable object that is then handling the container for us. Here in both in North America, we have different workers spun up that are then hitting the same durable object for the container. And then in Asia, they get their own durable object because that's a different continent. Each durable object acts as a programmable sidecar that can proxy requests to the container and manage its lifecycle. This allows you to control and extend your containers in ways that are hard on other platforms. Okay, so this is showing here our worker is technically like managing the durable object, and then the durable object is closely linked to the container. So our durable object is kind of like our interface into the container from a worker, which is interesting. You can manually start, stop, and execute commands on a specific container by calling RPC methods on its durable object, which now has a new object at this context container. So here is our durable object and our methods inside. We have a custom boot. So this container start. Okay, so this is a custom container starting function, basically. We have a function for stopping a container. So we'll pass it the code 15 as a signal into the container to make it stop. And then we can also have like a backup script. So we can call inside the container a CLI. This is using exec. So this is calling our backup script effectively sitting inside the container, but we're calling this from a durable object. I think this is really cool and powerful, but like this is adding just like so many different layers of abstraction here. So we have our container, and that's like already an abstraction of an entire operating system. Your container literally is just like a programmatic way of defining how an operating system should be set up to run your code. But now you're tightly linking that to a durable object which is then communicating back and forth from the container. And that is kind of like managing the state of the container. And then you have your regular workers, so like your Lambda functions, then reaching out and making any other calls that you need to actually be able to communicate to the durable object. That's kind of a mouthful, and I get why they architected it this way. It is powerful, but I wish you could just go, okay, here's my container. Don't worry about a worker. Don't worry about a durable object. I just want to run a container, because that's what you get with these other platforms. I mean, you can run containers on any major cloud provider. I think Cloud Run, and then I think Bunny is a really good example of just being able to give it a container image and have it spin it up and manage the scaling for you with very, very minimal configuration. But I digress. For instance, say you have a CI job that runs builds in a container. You want to post a message to a queue based on the exit status. You can easily program this behavior. So we have the constructor for our durable object, and we're giving it an on container exit function that adds to a queue of status success, build complete. Otherwise, if the container errors, it'll add the status error with the message to the queue. And then we have our start and monitor functions here. Okay, so this is probably this is where we're attaching our effectively logging functions to our container here. So we're monitoring the container, and then on complete, when the promise is complete and succeeded, it'll call our container exit. And then when there's an error thrown, it'll call our on container error. And then we also have an is running function that'll return if the container is actively running. Okay. And lastly, if you have state that needs to be loaded into a container each time it runs, you can use status hooks to persist state from the container before it sleeps and to reload state into the container after it starts. That's really cool. Let's see how they did this. So again, we have our durable object. Okay, this context block concurrency. So I'm assuming this is preventing concurrent requests from happening. So you don't end up with the race conditions. Okay, we're calling SQL in here. We're creating the table. Okay, this is inside their constructor. So we're saying when the durable object boots up, we can create a table and we can insert data into the table. And then we can wait for the container to respond on this port. So make sure the container's healthy, and then set up our monitoring. And then after it's set up, we can call setup container. I guess they're getting the point across on like the power of being able to run code based off of the life cycle of the container. Okay, and then when the container exits, we can respond with the container state. Also interesting to notice here, we're making a fetch request to just container. So it looks like that is going to be an available host name inside of your durable object. So that would be how you handle networking. Okay, and when the container exits, we update the state to whatever the state is currently at that point. Okay, cool. Building around your containers with workers. Not only do durable objects allow you to have fine-grained control over the container lifecycle, the whole workers platform allows you to extend routing and scheduling behavior as you see fit. Using workers as an API gateway. Workers provide programmable ingress logic from over 300 locations in the world. In this sense, they provide similar functionality to an API gateway. For instance, let's say you want to route requests to a different version of a container based off of information in a header. And you would do something like this for managing API versioning. So let's say you have a REST API and then a mobile app. You'll probably end up running a few different versions of your REST API at a single time, because your actual mobile app won't always be updated like your web app will be. And you could have breaking changes. So your mobile app could request a specific version of your REST API. And that's a pretty common pattern. And I'm curious to see how this can solve that and make it a little bit easier of a workflow. So here it's saying in our fetch request, it's supposed to be in our worker, we're checking if there's an experimental flag or header set on X version. And then if it's an experimental, we can call the specific experimental version of the service, otherwise standard. Cool. or you want to rate limit and authenticate requests to the container. So this is all about acting as an API gateway. So this is saying we can do our authentication in our worker, which is fast, very much global, and cheap. So we can have our worker as acting as the API gateway, authenticate all requests before they actually hit the container. This is cool. So yeah, and like I just said, so this is just saying, hey, authenticate the requests as they come in. If they're not authenticated, immediately return the status of 401. Otherwise, we do the rate limiter based off of the user's token. And then if everything is good, we just return the response from, I'm assuming this is our container here. Cool. That's a really cool pattern. So you can basically treat the worker as like middleware to your container, which is pretty sweet. Okay. Using workers as a service mesh. So here we see the life cycle. Our user hits a web request to our worker. The worker requests our object, and then it sends encrypted the message to the ingress proxy process, which is then decrypted to the container. So see, this is kind of what I'm talking about though, with this just being very much abstracted and might be too many layers of abstraction here. Because like you could do this where it's just the user going to the container or just the user going to a proxy and then a container. But here you have two effectively extra layers in between the user and hitting the container. I'm curious if these two parts have any effect on the latency, like measurable impact. And just that makes me a little concerned, like these two pieces of this would need to have like really good reliability, or else it's just like another point of failure. But it's Cloudflare, I guess they kind of have that thing figured out. Okay, by default, containers are private and can only be accessed via workers, which can connect to one of many container ports. From within the container, you can expose a plain HTTP port, but requests will still be encrypted from the end user to the moment we send the data to the container's TCP port in the host. Due to the communication being relayed through the Cloudflare network, the container does not need to set up TLS certificates to have secure connection in its open ports. Okay, that's really cool. You can connect to the container through a WebSocket from the client too. So this solves so many problems that serverless has today. Like just having WebSockets be available like natively on the platform is huge. This is cool. So just as the durable object can act as a proxy to the container, it can also act as a proxy from the container as well. Oh, okay, cool. So it's like a double middleware effectively, like it's your ingress and egress proxy. When setting up a container, you can toggle internet access off and ensure that outgoing requests pass through workers. So here, when we're starting the container, we're disabling internet. So here, I guess this is saying for both ingress and egress, or just egress at this point, it's just turned off and it has to go through the worker. So here, when the container requests, so this is saying the container doesn't have access to anything but requests coming from our worker here. And this is on our container request. I'm assuming this will be called anytime the container is trying to make a request. So like we can set the header of the container. Is that what this is saying? You can ensure all traffic in and out of your container is secured and encrypted end to end without having to deal with networking yourself. So we have our Cloudflare network. We have a service A, service B. These have their containers running in them, as well as our egress proxy and our ingress proxy. And then between these two pieces is not encrypted, I'm guessing, as I'm saying. But then between our service and the durable object, that is encrypted. So even just leaving service A to go from durable object to service B, that is encrypted at this point. I believe if I'm reading this correctly. You can correct me if I'm wrong. This allows you to protect and contain or connect containers within Cloudflare's network, or even when connecting to external private networks. Using workers as an orchestrator. You might require custom scheduling and scaling logic that goes beyond what Cloudflare provides out of the box. We don't want you to have to manage complex chains of API calls or writing an operator to get the logic you need. Just write some worker code. For instance, imagine your containers have long startup periods that involve loading data from an external source. You need to pre-warm containers manually and need control over the specific region to pre-warm. Additionally, you need to set up manual health checks that are accessible via workers. You're able to achieve this fairly simply with workers and durable objects. So we have our durable object and we have a scale function, which is okay, cool. So for every instance, so we're getting the region and how many instances we should have. And then for every instance count, we're spinning up a new container and we're giving it the location hint and we're starting it. So this is effectively pre-warming it here. And then down here in our container class, we have on start, we run a health check every half second. And then here is our health check function. Cool. So this in code lets you control your scale. So like programmatically in your code, you could say scale this to 1,000. Which is just wild. That's such a cool workflow. The container manager durable object exposes the scale RPC call, which you can call as needed with the region and instance count, which scales up the number of active container instances in a given region using a location hint. This schedule code executes a manually defined health check method on the container and tracks the state in the manager for use by other logic in your system. These building blocks let users handle complex scheduling logics themselves. We are excited to see patterns you come up with when orchestrating complex applications built with containers, and trust that between workers and durable objects, you'll have the tools you need. Integrating with more of the developer platform. So since Developer Week 2025, we would be remiss not talk about workflows, which just went GA, and agents, which just got even better. Let's finish up by taking a quick look at those. So let's say you need to download a large file from R2, compress it, and upload it. You want to ensure that this succeeds, but don't want to write retry logic and error handling yourself. Additionally, you don't want to deal with rotating R2 API tokens or worry about network connections. It should be secure by default. This is a perfect opportunity for a workflow using containers. The container can do the heavy lifting of compressing files, and then workers can stream the data to and from R2, and the workflow can also ensure durable execution. So here we have our encoder workflow, which is extending the workflow entry point class. And when it runs, we're getting an event and a step, and then we're getting container, step that do, we're setting up the container, and then we're compressing the object. Okay, so here we ensure the container is healthy. We'll get the payload, which is our R2 path, and then the result is, so here again, okay, so our encoder here is a container, and this is how we're calling it. Interesting. So we're calling encoder with the body, which is our R2 object here. And then with our artifacts, we're uploading the compressed file. Then our next step is to clean up the container, which is just to destroy it. So I haven't looked into Cloudflare workflows yet, but I guess it sounds like these steps can individually fail and then act as checkpoints. So if our container setup fails, it will restart here. If our compress the object fails, it'll restart here because it'll already have a container running. So this is cool and very common on this type of workflow. Although I am curious if there's more control on like how many times it'll retry before it fails, or if there's like I'm blanking on the name, but like how frequently it'll retry. Like if you can set the delay in the number of seconds on how long it should wait between trying. Calling a container from an agent. Lastly, imagine you have an AI agent that needs to spin up cloud infrastructure. To do this, you want to use Terraform, but since it's run from the command line, you can't run it on workers. By defining a tool, you can enable your agent to run the shell commands from a container. Okay, this is awesome. So create external resources. So this is a tool. Get a description and then give it the Zod definition of what should be passed into the tool. So you'll have to like create the schema for the CLI tool, and then you can execute it. So here we're creating the tool that the agent or the LLM will be able to then like read the description of, read what information it needs, and then call it and handle that for you. That's cool. And I like that that's all built in within one platform here. Okay, so then here is our exposed RPC method. Containers are so much more powerful when combined with other tools. Workers make it easy to do this in a secure and simple way. Pay for what you use and use the right tool. The deep integration between workers and containers also make it easy to pick the right tool for the job with regards to costs. With Cloudflare containers, you only pay for what you use. Charges start when a request is sent to the container or it is manually started. Charges stop after the container goes to sleep, which can happen automatically after a configurable timeout. This makes it easy to scale to 0. Okay, we can scale to 0. Good. And allows you to get high utilization even with highly variable traffic. So containers are billed for every 10 milliseconds that they are actively running at the following rates. Unlike workers, where they will only bill you for CPU time, it sounds like here you will just be billed for the overarching runtime on how long it took or how long it stayed active effectively, which makes sense. So there's the pricing. When with this many zeros, and when you're charging per GB second, I just have no clue what the scale actually looks like. That's kind of one of the challenges here. Like you can't just like estimate, oh, this is going to cost $20 to run this service. But I digress. After 1 terabyte of free data transfer per month, egress from a container will be priced per region. We're working out the details between now and the beta, and we'll be launching with clear, transparent pricing across all dimensions so you know where you stand. Workers are lighter weight than containers and save you money by not charging you when waiting on I/O. Okay, yeah, like I said. This means that if you can, running on a worker helps you save on cost. Luckily, on Cloudflare, it is easy to route requests to the right tool. So they're going to do a cost comparison of the two. Oh, with other platforms. Okay, interesting. Comparing containers and function services on paper is always going to be an apples to oranges exercise, and results can vary so much depending on the use case. But to share a real example of our own, a year ago when Cloudflare acquired Baseline was a heavy user of AWS Lambda. By moving to Cloudflare, they lowered their cloud compute bill by 80%. Below, we wanted to share one representative example that compares costs for an application that uses both containers and serverless functions together. It'd be easy for us to come up with a contrived example that uses containers suboptimally on another platform for the wrong types of workloads. We won't do that here. We know that navigating cloud costs can be challenging, and that cost is a critical part of deciding what type of compute to use for which pieces of your application. In the example below, we'll compare Cloudflare containers plus Cloudflare workers against Google Cloud Run, which I think is just like the most comparable alternative right now. I really wish AWS had a better alternative to Cloud Run at this point. A very well-regarded container platform that we've been impressed by. So here's our example. Imagine you run an application that serves 50 million requests per month, and each request consumes an average of 500 milliseconds. Requests to this application are not all the same. Half the requests require a container, and then the other half can be served using serverless functions. Container pricing on both Cloud Run and Cloudflare containers. A container can serve multiple requests. On some platforms, such as Lambda, each container instance is limited to a single request, pushing cost up significantly as the request count grows. In this scenario, 50 requests can run simultaneously on a container with 4 gigabytes of memory and half of a CPU. This means that to serve 25 million requests of 500 milliseconds each, we need 625,000 seconds worth of compute. In this example, traffic is bursty and we want to avoid paying for idle time. So we'll use Cloud Run's request-based pricing. So for Cloudflare containers, that would end up costing you $20. And Google Cloud Run would end up costing $23. So the pricing is very similar here. Compute pricing for both platforms are comparable, but as we showed earlier in this post, containers on Cloudflare run anywhere on demand without configuring and managing regions. Each container has a programmable sidecar with its own database backed by durable objects. It's the depth of integration with the rest of the platform that makes containers on Cloudflare uniquely programmable. And that is cool, although the biggest downside to Cloudflare's database product right now is that it has a limit to like 10 gigs. It's really designed to do multi-tenant applications where like one user would have their own database for like if it's a notes app, like their database of notes, because they would never, exceed 10 gigabytes. But like if you're building any major product right now, this just has no good use case because a limit of 10 gigabytes is just like nothing. Like it's really just not built for more larger scaled applications, in my opinion. Okay, function pricing. The other requests can be served with less compute and code written in JavaScript, TypeScript, Python, or Rust. We'll use workers and Cloud Run functions. These 25 million requests are also run for 500 milliseconds each, and each request spends 480 milliseconds waiting on I/O, which is very reasonable. This means that workers will only charge for 20 milliseconds of CPU time, the time that the worker actually spends using compute. This ratio of low CPU time to high wall time is extremely common when building AI apps that make inference requests, or even just building a REST API and other business logic. I agree. Most time is spent waiting on I/O. Based on our data, we typically see workers use less than 5 milliseconds of CPU time per request versus second of wall time. The Cloud Run function will use an instance with, whatever small. Wow, I didn't know you could like divide CPUs like that. But cool. And 128 megs of memory and charge on both CPUs and gigabytes or gigabytes for the full 500 milliseconds of wall time. So here, since we're not paying for the wall time with Cloudflare workers, our total cost ends up being $8 for a Google Cloud Run. Our total cost ends up being 11. This comparison assumes you have configured Cloud Run functions with a max of 20 concurrent requests per instance. On Google Cloud Run functions, the maximum number of concurrent requests an instance can handle varies based off of the efficiency of your function and your own tolerance for tail latency that can be introduced by traffic spikes. Workers automatically scale horizontally and don't require you to configure concurrency settings and run in over 300 locations. So here it says it uses a single tier 1 GCP region too. So Cloudflare is saying this is the cost for Google if you're running in a single region, but their workers won't charge you for the wall time, and they also will automatically be globally distributed, which is awesome. A holistic view of costs. The most important cost metric is the total cost of developing and running an application. And the only way to get the best results is to use the right compute for the job. So the question boils down to friction and integration. How easily can you integrate the ideal building blocks together? As more and more software makes use of generative AI and makes inference requests to LLMs, modern applications must communicate and integrate with a myriad of services. Most systems are increasingly real-time and chatty, often holding open long-lived connections or performing tasks in parallel. Running an instance of an application in a virtual machine or container and calling it a day might have worked 10 years ago, but when we talk to developers in 2025, they're most often bringing many forms of compute to the table for particular use cases. This shows the importance of picking a platform where you can seamlessly shift traffic from one source of compute to another. If you want to rate limit, serve server-side rendered pages, API responses and static assets, handle authentication and authorization, make inference requests to AI models, run core business logic via workflows, or ingest streaming data, just handle the request in workers. Save the heavier compute only for where it is actually the only option. With Cloudflare workers and containers, this is as simple as an if-else statement in your worker. This makes it easy to pick the right tool for the job. Yeah, this is cool. So this is like marrying your serverless functions with your serverless containers. So it gives you the option to reach for a full fat container to do your heavy workloads, like your FFM pegs. But when you're just doing like the regular day-to-day, you're getting requests, you're responding to requests, you're rendering pages, that can still be just handled by your workers, your serverless functions, which is really what they're built to do the best at and scale the best at. Coming June 2025, we are collecting feedback and putting the finishing touches on our APIs now, and we'll release the open beta to the public in late June 2025. From day one of building Cloudflare Workers, it's been our goal to build an integrated platform where Cloudflare products work together as a system rather than just as a collection of separate products. We've taken this same approach with containers and aim to make Cloudflare not only the best place to deploy containers across the globe, but the best place to deploy the types of complete applications that developers are building that use containers in tandem with serverless functions, workflows, agents, and much more. We're excited to get this into your hands soon and stay on the lookout this summer. This was a long article, but I'm happy I read it. I think I'm into it. I think it's a good idea. I still don't love the syntax of managing the containers and having to do it like within, you can really, only do it within JavaScript as far as I'm aware, but at least then you get the benefit of it all being like in one ecosystem. And I think AWS really dropped the ball on this. Like, it's nice you can use AWS libraries with like any major language, but I don't know, the teams just feel so disjointed, and it doesn't really give you like a unifying feel on like everything is connected, versus this seems like everything's perfectly integrated. Like here, we're just importing two things from a single package. And if that was AWS, you'd be importing like 3 to 4 lines from different packages just to get a basic hello world going. Yeah, well, we'll see once it's fully out and the API is actually like nailed down what it's all going to look like. But I am very excited for this to come out, and I'm excited to build a serverless FFmpeg container that automatically scales. Let me know what you think about this in the comments, and peace.